Yeah, although the first 5 minutes in my talk are just fun stuff before we get into the more important stuff. But let's wait. Yeah. The traffic has become worse. I first came in.
Good afternoon, everyone. Welcome to the IEEE Distinguished Lecture and Network Seminar Series hosted together by IEEE and Center for Networked Intelligence at the ECE and RVCCPS IAC. It's my pleasure to introduce today's speaker, Dr. Kumar Vijay Mishra. He will be speaking on signal processing for integrated sensing and communications. Dr. Mishra earned a PhD in electrical engineering and an MS in mathematics from the University of Iowa, an MS from Colorado State University while working on NASA's GPM-GV weather radars, and a BTech with gold medal honors from NIT Hamirpur. He is a senior fellow at DEVCOM ARL, research scientist at the University of Maryland's ISR, technical advisor to Hertzwell, and honorary research fellow at SNT, University of Luxembourg. He previously held research appointments at DRDO, LRDE, IIHR, MERL, Qualcomm, and Technion. He has served as the distinguished lecturer of various IEEE societies, won multiple awards, and has been committee chair and editor for major IEEE journals. His interests include radar, signal processing, remote sensing, and electromagnetics. Over to you, Dr. Mishra.
Thank you. I was just afraid if you were going to read the whole thing. All right. Good afternoon, everyone, and thank you very, very much for inviting me for this distinguished lecture, which also happens to be the Integrated Sensing and Communications, or ISAC, also known as communications, many names, which has seen explosive growth in research in several fields of electrical engineering in past few years. Now, it's me to, is this working? It's very difficult for me to summarize of research problems in ISAC in this roughly 50 to 55 minute talk. So what I'm going to do today is, first we'll start from a historical overview and then I'll take one representative example of one of ISAC topologies. We'll cover 3 topologies. And then in the end, I'll give you a very brief snapshot of different strands in ISAC research that are emerging these days. So hopefully that will give you a very good idea of what people are working on in ISAC and what we have done in this area so far. All right, there's a little bit about myself, but you have already read it. I only want to emphasize that apart from my role at ARL, I'm a technical advisor of these 2 very promising radar startups. First is Hertzwell, which is based in Singapore. It is Asia's first automotive radar startup, and I've been associated with them right from its inception in 2018. Second is Aura Intelligent Systems. It's a radar startup, which is very much related to what we are going to discuss today. That is the use of 5G waveforms for sensing and especially imaging. And it is based in Boston, Aura Intelligent Systems. My primary research interest is in radar, and I explore its connections with signal processing, electromagnetics, wireless communications, and remote sensing. I would like to acknowledge a number of my colleagues whose collaborative research is going to feature in the talk today. They are all listed here, as well as DEVCOM, ARL, and the US National Academies for funding most of my research for past few years. Now, I don't know if this is working or not. It's working? Okay. Now, in my talk, just to keep things interesting for students, I like to put snippets from my favorite science fiction TV shows and movies where the characters are talking about radar that you'll see throughout this presentation, just to keep you engaged if you find rest of the content not very interesting. But the snippet that you see on this slide is very much related to what we are going to discuss today. This scene is from a very popular Apple TV Plus show, For All Mankind. It's about a bunch of NASA scientists. It is set in 1960s in an alternative fictional historical timeline. And in this scene, these 2 scientists, they are discussing the effect of solar flares because of increased sunspot activities in early 1960s on communications receivers. So apparently that kind of radiation could jam the communication receivers. This is an example of natural interference on electronic systems. Of course, today we are going to discuss about the man-made interference, that is interference from another emitter like radar, navigation or positioning system on communications and vice versa. However, if you go back to early 1960s, and this is hard science fiction, so there used to be an IEEE journal, IEEE Transactions on RF Interference. It was discontinued later on, but a number of papers that were published in that journal were exactly about this problem, that is the effect of solar flares on communications receivers. So clearly there have been studies on RF interference that have been present in the decades. Because there is interference from one system to another, if they are operating in the same part of the spectrum, an obvious solution could be, let's come up with a multifunctional hardware that can perform those functionalities such as communication, sensing, and others using the same type of hardware and the same waveform. So if you look into the literature, a very early form of joint radar communications which can emulate this kind of together, you can find it in the literature also in early 1960s. So that is a elementary joint radar communications system that we find in this 1963 paper. Then in late 1970s, NASA explored this concept for their space shuttle program, because anything that you launch into space, it has constraints of power, space, cost, energy. So you want to minimize the hardware, you want everything to be compact. So they looked into joint radar communications, and then we see some literature in 1970s. However, it was not until mid-1980s that this problem was looked into a little bit more intensely by our electrical engineering community. So in mid-1980s, US Army started deploying this type of radar that is used to detect intruders in very thick vegetation areas like forests and so on. And when they started deploying it, it operates in the UHF-VHF frequency band, which is also used by the TV and broadcast stations. So that radar started encountering a lot of interference from those stations. Since the transmit bandwidth of this kind of radar is extremely wide, engineers came up with a simple solution that let's put notch filters at the location of interfering frequencies at the receiver, and that worked very well. But you would see a lot of work on this topic by Mark Davis people in that era. Then in early 2000, this problem was looked into a little bit more by the defense communities. But in years that we have seen a lot of work coming out on ISAC and all the research that you see nowadays, that is all in last 10 years, I would say. So the real question now is, what is it that has changed in last 10 years, despite decades of awareness about RF interference, that we are researching ISAC more these days? So there are a lot of driving factors behind this research, but I'm going to discuss two primary factors now, one from the communications industry and another one from the radar sensing side. So if you look into the recent trends in wireless communications, as you can see from this graphic that I've taken from some industry sources, the number of devices that are connected right now, that number has crossed hundreds of billions, and it is supposed to dramatically rise in near future. More devices being connected means more data are being exchanged, and then you need a protocol that can support those kind of high data rates. Apart from this, we have expectations from future 5G or so-called 6G networks that they provide very high quality of service and also support the futuristic applications related to infotainment and gaming. All of that requires very high data rate, which the current conventional sub-6 gigahertz cellular regime is unable to support. So how can we meet this demand? For that, we turn to our Shannon's famous capacity formula as a guide, which tells us that the capacity C, which dictates the data rate, is governed by these three factors. SINR, you'll have to increase it a lot to see any appreciable increase in capacity C, because they have a logarithmic relationship with each other. We can also use lowercase n, which is the number of orthogonal or non-interfering resources, like number of time slots, number of subcarriers, number of transmit and receive antennas. And then the third factor that we can work with is bandwidth B. So, or W. Wider the bandwidth, higher will be the capacity, but we know that electromagnetic spectrum is a scarce natural resource. So we cannot arbitrarily allocate it to just one service provider or for just one application. What happened? I don't see this. Okay. All right. Okay, so about the bandwidth. All right, so you need wider bandwidth if you want to support these high data rates. And as you that I've taken from Ericsson's white paper published a few years ago, currently sub-6 gigahertz part of the spectrum is extremely crowded, and that's where we are seeing there have been more work in the traditional communications area. One way that you can increase this bandwidth is that you move to higher frequency bands like FR3, lower millimeter wave, or upper millimeter wave, which we also call it as low terahertz part of the spectrum, where depending on which country you are in, you can get anywhere from 4 to 15 gigahertz of contiguous bandwidth. So that's a lot of bandwidth. But then you also have to develop technology to operate in those high frequency bands, because attenuation increases with frequency, although that increase is not linear. Now, this contest of wider bandwidth, it is actually not new among communication service providers. I've taken some headlines here from, okay, I have to go back to this. I've taken some headlines here right from 19 until very recently, that wireless service providers, they have been asking for more bandwidth from their governments for decades. And this problem is only as new service providers, they enter the communications protocols that come up. Second motivation for ISAC comes from the radar industry or now, as far as radar is concerned, radar has been using pretty much all parts of the spectrum, right from its invention during the Second World War. So we have radars that operate at UHF, VHF all the way to terahertz band. But what is different now are some new applications, especially automotive radar. As you can see from this graphic, autonomous vehicles, they are highly sensor driven. They are equipped with LiDAR, GPS, radar, cameras, ultrasonic sensors, and so on. And the goal of these sensors is not only to guide the driver or that autonomous vehicle in a crowded or challenging traffic environment, but also to monitor the general health of the car. So there are a lot of sensors that monitor tire pressure, air conditioning, and so on. And then sometimes also to monitor the physiological behavior of the driver or other occupants of the vehicle. So we have in-cabin non-contact sensors that can measure the respiration rate, drowsiness, they can detect drowsiness of the driver, and so on. So if we want to enable full autonomy, we need all these sensors. But if we just focus on the driving part, on just the autonomy part, chiefly three sensors are common. So you must have seen high-resolution camera. It is now deployed on many cars, provides very good visual of the surroundings. However, its disadvantage is that when the visibility conditions are low, whether in the night or in the presence of precipitation like rain or snow, then obviously its performance deteriorates. More importantly, when you're on the road, then you want very accurate measurements of your surroundings. It's a life or death situation. However, a camera cannot very accurately give an estimate of something as simple as Doppler velocity. It only indirectly infers it by looking at the displacement of its targets across the frames of the video. And this can cause a lot of problems. So here's a headline from Washington Post last year. I blurred the name of the vendor, but I think if you know which is a very famous vendor that relies only on cameras for autonomy, then it can cause these kind of problems. Then because of these problems, we move to the remote sensing sensors, for example, LiDAR and radar. Now, LiDAR provides the highest resolution. For people who may be familiar with the remote sensing signal processing may recall, wider the transmit bandwidth of the signal from these sensors, higher will be the resolution. By resolution, we mean here the ability to discriminate between two very closely spaced targets. So LiDAR has the highest resolution because it operates in the optical part of the spectrum where a lot of bandwidth is available. The problem with LiDAR is, first, it's very expensive. A few years ago, General Motors had released a white paper which stipulated that the cost of remote sensing sensors should not exceed $100 in batch production, and LiDAR simply does not meet that benchmark. In fact, its cost is in thousands of dollars. And the second problem is that it's a mechanically scanning device, although there's a lot of research and PhD theses I see these days on electronically scanning LiDARs. It's really not commercially viable at this point of time. Because of these problems, we move to the third sensor, which is radar. So radar operates in the microwave part of the spectrum, because of which its bandwidth is somewhat limited compared to LiDAR. So narrower bandwidth means poorer resolution. So that is the biggest problem with radar these days. It has other advantages. It operates on Doppler principle, so it can measure it directly, unlike a camera. It's a cheaper sensor compared to LiDAR, and it's an all-weather sensor as far as automotive radar is concerned, because there the range of the radar is up to about 200 meters. So even in the presence of precipitation, attenuation is not very significant at the frequencies that automotive radar operates. But it has this very poor resolution, and the only way we can increase it is by allocating more bandwidth to radar. But we just discussed bandwidth is not freely available, so we have to find a way to share this bandwidth with other service providers and other applications. All right, so with that as the background, why people are looking into ISAC more nowadays because of these changes in applications or developments of new protocols. Now we are going to look into what kind of ISAC topologies have been developed in past few years, what solutions are available, not the notch filter kind of solutions, but solutions that address more complicated and sophisticated needs of spectrum and these kind of electronic systems nowadays. And then I'll take one example each, one of coexistence type of topology, co-design, and then finally opportunistic ISAC. And as we move from coexistence to opportunistic ISAC, we will also move from a highly theoretical signal processing example to a very practical example. So that will give you both sides of the story, theory as well as practice. All right. First thing we want to look into is how worse this problem is. Of course, automotive radar and wireless communication people, they are facing this problem. But is it really a very serious problem? Turns out it is. As you can see from this table, pretty much every IEEE radar band today has some coexisting communication service. This was not the case even 20 years ago. We did not have X-band weather radars at that time. And this problem is only worsening because of new applications on both sides, radar and communications coming up. Now, this does not only have engineering or research implications, it also has legal and policy implications. So there have been two very famous court cases in the United States. I put some headlines there, which actually demonstrate how much problematic this has become outside of engineering or research. So the very first court case was in 2021, when Federal Communications Commission, or FCC, that is the regulatory agency which deals with spectrum allocation and regulations in US, decided to allocate slivers of sub-6 gigahertz band, which is a very crowded part of the spectrum, to unlicensed users. So anyone could transmit in that part of the band. Because of which AT&T decided to sue FCC with the contention that this is going to cause interference to the 5G service that they provide to their clients. In the following year, when Federal Aviation Authority, that is FAA, asked Verizon to stop transmitting its 5G frequencies around US airports because it was interfering with a device that airlines have been using for decades for landing and takeoff. And this is not even a radar. This example illustrates that the problem goes beyond radar and communications. That's a C-band altimeter. And Verizon then decided to sue FAA because they had paid billions of dollars in auction to operate or transmit in that part of the spectrum. Then there have been complaints from other communities as well. As you can see from some other headlines here, radio astronomers have been complaining about interference from communication satellites that hinder clean sky observations. There are concerns from meteorologists that sometimes Wi-Fi shows up as interference on the radar screen and causes incorrect or inaccurate weather forecast, because sometimes it can be inferred as a tornado given the signature it provides on the radar screen. So recognizing all these kind of implications, about 12 years ago, DARPA, which is a defense funding agency in the US, decided to launch this program called S-Spark. That is to develop spectrum sharing technologies between S-band military radars and S-band military communications. And after the success of S-Spark, National Science Foundation has been expanding this investigation across all the bands, and they have launched several programs that you see here. Some of those are listed here, and every year I see a new call of proposal from NSF to address some part of the spectrum management. So that shows this problem is actually pervasive. It goes across the standard radar and wireless communications communities. Next, we to look into what kind of solutions have been developed since the launch of S-Spark program. So not the notch filter, but what else is available. For that, we'll have to classify these kind of solutions into certain categories, just so that we can easily cover most of them in this talk. A very simple way could be, because we don't want interference from radar to communications or vice versa, let's come up with a joint hardware. Let's have a common transmitter, a shared transmitter, or a shared receiver, or just a shared transmitter, but because of some other applications, you don't want the receiver to be shared, and so on. Based on that, we can classify these solutions very, very broadly into these 4 categories. So this figure is from our very popular IEEE signal processing magazine paper. So depending on whether the transmitter receiver is shared or not, you get these 4 types of topologies. Figure A is the case where the hardware is not shared at all between either at the transmit side or receive side between radar and comms. In that case, radar and comms, they transmit independent of each other. Obviously, there's going to be interference at the receiver. Most of the signal processing research in this case is then designed to mitigate mutual interference without change of hardware. This approach is called spectral coexistence. It was very popular during the early days of ISAC. It still is. Because for legacy systems which have already been deployed in very large numbers, it will cost a lot to change their hardware. So the decision here is let's just focus on the digital side and develop new algorithms that can mitigate mutual interference. Even though it was an early approach or a simplistic approach, that by no means implies that this is an easy signal processing problem. In fact, the very first problem that I'm going to tackle very soon is spectral coexistence problem, and it will show how the signal processing could be very complex for that. Everything else where some hardware is shared is spectral co-design. A very general version is figure D, which is for an automotive or a traffic scenario. So here I have a red car, which is a common transmitter. It is transmitting a radar waveform with communication symbols embedded in it. That waveform then interacts with other cars in the environment, like the blue car or the yellow car. We'll call them radar targets. When it is reflected off from those radar targets, it is intercepted by a common receiver on the gray car. And the job of signal processing for that gray car receiver is twofold. First, to extract parameters of the radar targets like Doppler velocity, location, range, and so on. And second, to decode the message that was sent by the red car, because it is also a communications receiver. Static joint radar communication system. Transmitter and receiver, they are on 2 different platforms. You can extend this to multi-static case and so on. It has been about 10 to 12 years of SPARC, and if we have just 4 categories and thousands of people working in this area, then they would have found solutions to these problems. So why we are seeing so much work these days? So my answer is, recall that I mentioned this is a very, very broad classification. In fact, there are so many other criteria that exist based on which you get a different ISAC topologies. So I've listed some of them here. We already saw based on hardware, you can classify them in 4 categories. You may have a common waveform, or they can have separate waveform but still sharing the same hardware. So you will get different. Example of bistatic, you can extend to multistatic, they may or may not be networked, many different solutions. Normally, when we are looking into joint radar communications, our objective is to optimize the performance of both systems equally. But there could be some cases where we are all right with accepting deterioration in the performance of, say, communications, while optimizing primarily the radar-centric solutions. Vice versa, you get communication. Interesting case is opportunistic ISAC. We'll see one example toward the end of this talk, where we don't want to change any hardware. We want to use existing infrastructure of one functionality, let's say communications base stations, and then repurpose them for the second functionality, that is radar. And then there are all kinds of specialized using sparse reconstruction. Then there's a whole different category of solutions, learning-based solutions. Reconfigurable intelligent surface is very popular these days, and it is RIS-aided ISAC has become an area of its own. Sometimes we also classify depending on which part of spectrum we are working on. So we'll see one example of millimeter wave ISAC in the co-design case. There's a lot of work on terahertz ISAC, some work also from visible light community. Not exactly ISAC, it's joint visible light communications and visible light positioning. And then recently we have seen some work from the quantum community, joint quantum sensing and quantum communications. In fact, about 15 different IEEE societies have published literature on ISAC or have some task group that is looking into this, including non-IEEE societies like Optica, AGU, AMS, ERSI, and so on. That should tell you how popular this problem is, and if you are a new master's or PhD student, it's a very good topic to pick up for your thesis. All right, so we have looked into different classifications. Now let's take one example each. So we'll start with spectral coexistence first, then co-design, and one opportunistic ISAC. For spectral coexistence, I have chosen this example of dual blind deconvolution that we have been working at US Army Research Lab for past 3 to 4 years. To understand what dual blind deconvolution is, very quickly, let's do a recap how normal radar and communications work. In a conventional radar, we transmit the waveform, so we know what waveform it is. We have full knowledge of the waveform. That waveform then interacts with the radar target, and it's a target call it radar channel, segment of the talk, is unknown. The received signal is a convolution of the known transmit signal with the unknown target profile. When we have the received signal measurements, with the knowledge of the transmit signal, we try to estimate the unknown target profile. This is standard radar signal processing. We know how to solve it. You can also call it a deconvolution problem. Now consider the case when someone else is transmitting the signal. In that case, you may not know that waveform. It could be a hostile entity, could be an enemy radar, may also be a signal of opportunity, like a Starlink signal that we don't know much about because it's proprietary and so on. In that case, at the receiver, you have the convolution of an unknown transmit signal with the unknown target profile. And by looking just only at measurements, you're supposed to estimate both of them. This is blind deconvolution, which has a very rich heritage of literature in signal processing right from 1970s. But in past 10 years, we have seen a lot of work on blind deconvolution, where people are leveraging theories of sparse reconstruction to solve it. In communications, you may have a similar situation. In communication, it's the channel that is estimated a priori, and obviously it's a transmit message that is unknown at the receiver. So that is deconvolution. However, as I'm talking about, let's move to the higher frequency bands and then vehicular communication. Now in those cases, coherence times of the channels are very short, and the channel is also very dynamic. It's quite possible that you may estimate the channel a priori, but that estimate may become outdated very quickly, and you will have the case of blind deconvolution even for communications. This is for radar and communications separately. Recall that in coexistence case, they are all superimposed. So and at the receiver. So in coexistence, we don't work on the transmitter, right? We are working mostly on the receiver. So when you have these blind deconvolution of radar and communication superimposed, then you get a problem of dual blind deconvolution. So you don't know about both channels, anything, or you don't have information about the transmit signals as well. You only have this received signal, and you're supposed to estimate all 4 of them. So intuitively, you can think of it as 2 people are talking with each other. We only hear the combined result. We don't know what they said, and we don't know how they sounded. So the channels are unknown, transmit signals are also known. So if I have to write this problem mathematically, it will be the first equation that you see on this slide. So I have these received signal measurements by t, superposition of 2 convolutions. So asterisk is for convolution. X and H, they stand for transmit signal and channel respectively, and the subscripts R and C, they stand for radar and comms respectively. So by looking at just YT, I'm supposed to find out all 4 convolvents. We know it's not possible to solve this problem. It's an ill-posed problem. There will be so many combinations of those 4 would map to the same YT. So how do we solve it? If you look into the single blind deconvolution literature, usually if we have some knowledge about the structure of these signals, then we can solve this problem, at least in the single blind deconvolution case. So at ARL, we approached from that notion that can we look into some of the common structures of this signal that are relevant for the army. So for radar channel, you see in the gray box, it's the standard target model. So assume L targets on the scenario. Each one of them is characterized by its complex reflectivity, which indicates the size, shape, or material, delay time tau r tilde, which is directly proportional to the location of the target with respect to the receiver. And in the exponential, you see the Doppler velocity, Doppler frequency nu r, which is directly proportional to the Doppler or the radial velocity of the target. That's a standard radar target model. For communications also, we assume a delay model, but with caveats. As far as transmit signals are concerned, for radar, we consider it's a very conventional pulse Doppler radar. So it is transmitting a train of pulses. We don't know the pulse ST. Sometimes, because it's blind deconvolution, you may also not know the periodicity of that pulse. But let's assume you could apply the period estimation algorithms to estimate that. And the only thing that is unknown is ST. For communications, we assume it's the popular OFDM signal. We don't know the message GP. We are going to estimate the message GP. We are not going to decode it or map it to a constellation. If you want to do that, then there are algorithms, known algorithms for that. So we'll just stop in this problem at GP. Now you take these 4 structures, put it in the first equation, and then after a few pages of tedious algebra, whose details you can find in our JSI paper that I've listed here, you get this last equation. So in this last equation, and you also sample it, digitize it, and then, like I said, after some more steps, you get this last equation, where now we have the structure at least, but we have a lot of unknowns. So we have all the channel parameters that are unknown, and the transmit signals as well that we don't know. Recall, even though in dual blind deconvolution, I don't know all 4 convolvents, really the quantities of the communications message and the target profile as far as radar is concerned. Although we'll end up estimating all 4, but actually those 2 are really of interest. And that is the case with most blind deconvolution problem. You may not know both convolvents, but really the interest is usually in estimating just one of them. All right, so now we have this structure. Next step is to estimate all of this. Before I tell you what I for some of these observations, first is that the channels are sparse. So obviously we are going to use sparse technique, some version of it. So channels are sparse, that means L and Q, they are very few compared to the number of signals that we are admitting at the receiver. Second constraint or observation that we can make from some of the measurements in radar and comms is actually on the transmit signals. So they are usually the constant envelope signals in spectrum. We can put this mild constraint that they lie in a known low dimensional subspace. This is the famous that we also see in phase retrieval and super resolution problems. What it will do effectively is that instead of solving for these unknowns sequentially, it will encapsulate all the unknowns for radar and communications in rank 1 matrices. So our job will become to recover those rank 1 matrices, 2 rank 1 matrices, instead of solving for all of these unknowns separately. So you apply the lifting trick, few more pages of tedious algebra, and you get this very compact sensing model that you see at the center of the slide. That is the discrete measurements Y. They are superposition of 2 linear operators, Aleph R and Aleph C, that is for radar and comms respectively, which are function of rank 1 matrix in ZC, which encapsulate all the unknowns of radar and comms. All right, we have this model. I'll tell you what we'll do in sparse reconstruction, but before that I want to draw your these rank 1 matrices. As you can see from this slide, the last equation, they contain complex exponentials. We know from Euler's formula you can write complex exponentials in terms of signs and we are dealing with trigonometric polynomials. So we'll use theories of trigonometric polynomials. I'll show exactly which solve this problem. Since it is sparse reconstruction, the very first thing that but in this case, sparsity is a little bit, it's in 2 systems separately. Both delay and Doppler domain. So it's in both. We'll have to use something else. We'll use the generalization of L1 norm, which some of you may also know is called atomic norm minimization. It was proposed about 14 years ago and has been very, very popular in spectral estimation algorithms. It allows you to generalize L1 norm minimization to arbitrary basis. So we'll use atomic norm minimization. So what we are going to do is the primal problem minimize the sum of 2 atomic norms, one for the radar case, one for communications, subject to the observations Y that we have. Now, in case of standard atomic norm minimization, as soon as you write the primal problem, immediately you can get the SDP. However, this is a little bit complex. There are superposition of 2 atomic norms, and those atomic norms are higher dimensional. They are not one dimensional because the sparsity was. So it is not straightforward to actually get these retrieval of these parameters from the primal. So what we'll do is, we observe that there are equality constraints in the primal problem. So as a result, in optimization theory, Slater's condition is satisfied and we have strong duality, which means if I can solve the dual of this problem, it will give me the exact solution to the primal problem as well. And sometimes looking at the dual, we don't know it yet. It may be straightforward to solve the dual problem. In fact, in this case, it is. If you look at the dual, it can be solved. But then before I tell you how the dual looks like, we need to recall that property of the trigonometric polynomial. So specifically, positive trigonometric polynomials, or PTP, this is a higher dimensional case. We call it positive hyperoctane trigonometric polynomial. In 2007, Professor Bogdan Dumitrescu of Tampere University, he published trigonometric polynomials and their signal processing application. So, and they have discussed a number of signal processing problems in that very nice book. So in that book, you come across this property that if you have a positive trigonometric is the complement, then you can characterize all the coefficients lowercase rk using a PSD matrix Q. So I can write Rk as the trace of the product of an elementary Toeplitz matrix and this PSD or gram matrix Q. What is, if I have an inequality, a positive inequality on trigonometric polynomial, if you are working with LMIs, then somewhere it may lead to STP. And as I mentioned earlier, this for one-dimensional, then you do it for the higher dimensional case, positive hyperoctane trigonometric polynomial, you can write a similar property. You can find the details in our paper. So this is what we did. So we had the primal, minimize something, equality constraints, you take the Lagrangian, work through and try to find out your dual problem. It looks like the first equation. So maximize that inner product subject to two inequalities. Now you take the left-hand side of that inequality, which is the dual of atomic norm. Take it on the right-hand side, 1 minus the dual greater than or equal to 0. You expand it. That is an inequality on a positive inequality on a trigonometric polynomial. So we can use that property from Dumitrescu's book and replace it with an LMI. You see in the sixth, although it looks complex, it is actually your. Now, in system identification problem in control, if you're working in that area, something similar there as well. So now I have the SDP, so I can solve it in my favorite programming language. The next question, there are the radar signals and comm signals. Okay, so if you solve this problem, you will get two, the output, two dual radar, one for communications. In our work, we have these dual polynomials and find the locations of the radar targets. Here. So I'll just explain what this means. So you get these two polynomials. They are function of delay and Doppler, because remember that you search for the peak of that polynomial, and wherever the maximum modulus of these polynomials, they achieve unity in the delay of your target and the comms paths. With the standard CFAR, you have the post-process signal, and then you compare it with certain threshold. If it is higher than that, you declare a target. If lower, noise or clutter. Here, that threshold is actually just unity within some numerical precision, whichever programming language or computer you are using. So within the numerical precision of that. So wherever this is unity, that will give you the location of your targets. After you have found the location of targets or the comms channels, then the problem is no longer blind deconvolution. Then you can use any one of your favorite methods. We use least squares to actually estimate the comms and the radar signals. So shown here is one such example where we have these two polynomials. I'm plotting their modulus in the delay Doppler plane, and then I'm zooming into the peaks. And the green circles is the ground truth. That's the target location or comms paths. And then plus sign is wherever it achieves unity. You can see plus is right on top of that green circle showing perfect recovery. This is a toy version of the problem really, because a lot of other constraints or other generalizations had not crept into this. So we have worked on generalizing this problem as well to other scenarios. For example, if I'm using a an array receiver or a multi-entity from data also have to recover DOA, direction of arrival. So it becomes a three-dimensional problem. But this whole machinery of atomic norm minimization that I've shown you just now, all of that could be extended to that case as well, to the 3D case. You may also ask what happens in the case of n-tuple blind deconvolution. So when we have more than 2 emitters, not one radar or one communications, but let's say 3 radars and 2 communications. So even in the case of n-tuple blind deconvolution, you can extend this. What will happen in the number of emitters you have in that problem. And then other generalizations, what happens when radar and comms, they don't transmit at the same time. In fact, that would be the case most of the time, but you don't know the lag between them. Then that lag becomes another unknown in those matrices that I described to recover. Finally, atomic norm minimization, because it requires SDP, it's computationally expensive. So our focus in the recent years has been to look into the low complexity algorithms. One of them is this low rank Hankel type matrix recovery, where we use theories from Berling-Selberg interpolation theory. So your Berling-Selberg majorant and minorant, which have been used in some other problems like super resolution before. We have actually generalized them for this dual blind deconvolution as well in our recent work. So you can find those details in the references that I have provided here. This was the case of spectral coexistence. Clearly, this shows that how very complex signal processing theories, they come into play even while solving a so-called simple ISAC problem. Let's now quickly look into one example of spectral co-design. So in spectral co-design, I've taken this example of automotive ISAC, and this particular problem was actually motivated by one automotive radar company, IEE, not IEEE, IEEE. That's an automotive radar company that we have been working with them for past many years. Recall in spectral co-design, we work on both sides, transmitter as well as receiver. Coexistence was just receiver. So here we also have to work on designing the waveform or examining what waveform we can use. So we will look into that bistatic case, the red car, gray car case, and this research was published in our paper in TAES, which was actually a runner-up for the IEEE Barry Culton Award 2 years ago. Now, in automotive case, automotive vendors, they are not very fond of using new waveforms. So clearly, in all these cases, you will come up with some optimization problem, and you can actually design a new waveform for automotive ISAC. But they're not very fond of using that because they want to use existing waveforms that can be modified slightly so that they are implementable on the chipsets that they have been using so far. So they wanted us to actually examine one of the existing waveforms that are used in automotive industry and then see if it can be used for ISAC or not. So we looked into 2 waveforms. One was radar-centric, another one was communication-centric. For radar-centric case, it was phase-modulated continuous wave, and for communication-centric case, it was OFDMA. PMCW has become very, very popular in automotive industry these days. IMEC has actually released a chip that implements PMCW waveform. It has this very nice property. Of course, it's PMCW, so you're sweeping a very wide bandwidth. You'll have very good resolution. But it's another one of its property is that its ambiguity function is a thumbtack shape. So for people who may not be familiar with what ambiguity function is, you take a transmit waveform and correlate it with its delayed and Doppler shifted replica. The result will be a main lobe and then some side lobes. Lower the side lobes, it's better because you can distinguish between 2 very closely spaced targets very well. So it has that shape. It provides a very good range estimation performance. OFDMA provides a very good Doppler estimation performance. So our first order of business here was that these properties, do they carry forward when we want to use these waveforms in a joint radar communications mode? For that, you need to rederive their ambiguity functions in that mode. So I'll spare you the derivation. You can find the details in our paper, but this is how they look like. If we examine them closely, it turns out that these children waveform, that is PMCW, OFDMA joint radar communications mode, they retain the properties of their parent waveform. OFDMA JRC still has a good Doppler estimation performance as OFDMA, standalone OFDMA, and PMCW JRC has a similar performance in case of range estimation. So now that we know this, we can use this information. We know these two waveforms could be used at least to retrieve some parameters in automotive radar. So the next case is, let's transmit these waveforms, let's do the modeling of the target scenario, and then let's receive processing. So at the receiver, we will have 4 unknowns. So let's very quickly look. So here's processing JRC. I want you to focus on that equation which has 4 summations. You will have 4 unknowns at the receiver: communications messages, angle of arrival, delay or range, and Doppler velocity of the radar targets. And it could be extended target scenario also. We have done that case as well, because in automotive, usually the targets should be modeled as an extended target. Now, it turns out in PMC-WJRC, you do your Fourier beamforming. Immediately, you get an estimate of angle of arrival. Since estimation performance filter, you get a very good estimate of range. Then you are left with 2 unknowns, Doppler and communication symbols. It turns out when you look at the residue coupled with each other, you cannot estimate them independently. So in our work, and this problem happens in most spectral co-design cases, people address it in different ways, sometimes in degrees of freedom and so on. So in our case, we suggested a form of multiplexing. Do not transmit joint radar communications waveform all the time. For some, transmit only the radar-only waveform. In that case, there is enough identity. You can estimate these 2 coupled parameters very well. So that's what we suggested here. Now in OFDMA JRC also a similar problem happens. Again, you will have 4 unknowns, angle of arrival, you estimate it using your Fourier beamforming. Here, Doppler is estimated first using FFT, but then it is the range that gets coupled with the communication symbol. So solution that we adopt is again similar. Do the multiplexing, but now in the subcarrier domain, not in the frame domain or the time domain. Reserve some subcarriers for radar-only transmission and rest of the subcarriers for joint radar communications. Then you can solve this problem. In fact, if you look at the overall system design of this kind of system, receiver is pretty much the same for both PMCW and OFDMA. First you do the coarse estimation of the uncoupled parameters, but it turns out it is accurate for those parameters. It's a coupled parameter for which it will be coarse. And then you have a communications receiver which is working on this joint radar communication symbols, trying to decode the communications messages. Then you pass that information to the radar processor. It removes it. Now, this communication estimation may or may not be perfect, and we'll see what effect it can cause. And after that, you do a fine estimation for the coupled parameter. So receiver is largely, the processing is same for both waveforms. Of course, the transmitter is going to be different. There are 2 different waveforms. The only common part is multiplexing, but it is in different domain, PMCW-JRC in the frame or the pulse domain, and OFDMA-JRC, it's in the subcarrier domain. The last slide that I want to show you in this segment is the performance. Now, because of paucity of time, we are not going to cover all 4 plots. I want you to focus on figure B, where I'm plotting the estimation error in the coupled parameter of OFDMA, which was, if you recall, it was range that was coupled. So with respect to SNR. So red curve is the case when there is no coupling. That's a theoretically best case. Of course, it won't happen in practice. We are just, communication symbol removal is perfect. So no coupling and no multiplexing, that is the red curve. Blue curve is the case when, that's in practice, when the coupling is happening, but we are not doing any multiplexing. You can see at high SNRs, it converges to the theoretically best performance, but these are not high SNR systems, especially radar. It's a low SNR system. So at low SNR, it diverges from that red curve. However, if you do multiplexing in the presence of coupling, which is the gray curve, here we are doing half subcarriers for radar, half for joint radar communications, then in than conventional receiver processing is required. Here we do multiplexing. In some cases, people, they choose to transmit radar in communications using different degrees of freedom, like do one polarization for radar, another one for communications, and then you have to have a receiver which can accept both polarizations, and then you do that processing separately. But if you don't have something like that, then you will end up with a problem like this. For automotive joint radar communications, there is just a whole lot of work that exists today in literature. We saw a case of millimeter wave, but then you can also look into that problem for the terahertz, low terahertz case, to work in that area. Where we have also used some learning algorithms. You have to think about some other technicalities in terahertz. So in millimeter wave, we were largely working on signal processing, but here you also have to look into the channel model. It is actually a little bit. Chandramurthy is sitting here. We have done quite work in this low terahertz automotive radar and joint radar communications with Chandra. And then very recently, we are looking into orbital angular momentum for ISAC. It's a very, very popular field nowadays, where you use another property, which is orbital, and then different modes are available in that. That's another degree of freedom that you can use to separate radar and communication. It's very, very popular topic, but I don't have time to cover an entirety of OAM GRC, maybe another time, but you can find more details in our paper. The last part that I want to touch upon is opportunistic ISAC very quickly. So we looked into coexistence, very theoretical example, co-design, automotive GRC, some practice and theory. Now let's look into this problem where we actually worked with some real data. Here I've chosen a problem for weather sensing. Recall in opportunistic ISAC, we want to use existing infrastructure without changing much in hardware and repurpose it for the other functionality. So we had this problem here that can we use communication satellite terminals for sensing weather? Normally, how do you estimate rainfall rate or sense weather? You use weather radars. These are huge S-band or C-band systems. In United States, National Weather Service operates a network of 140 S-band radars, which theoretically cover the entire country. In India, Australia, Europe and Canada, it's usually the C-band radar network that those countries use. But anyway, the principle is same. So S-band radar in US covers the whole country theoretically, but in practice, there are gaps in their coverage. If you take an S-band National Weather Service radar in US, its max range is 250 kilometers. But after 80 kilometers, the lowest elevation beam is already reaching the cloud tops. It is not observing the lower troposphere, which is where the rain events are happening. So in practice, then the same thing is available, same thing holds valid for C-band radar network also, except that what range that gap starts will be different. It will be actually much shorter. And then there are all these other developing economies where there is no weather radar. So we were approached by this, so there are a lot of global coverage gaps as well. So we are approached by this European telecommunications company. I'm not supposed to reveal the name of that company, but the problem was as follows. They had these communication satellite terminals. So the signal is coming from the satellite, passing through the atmosphere and getting ground terminals. As signal propagates through atmosphere, it interacts with the precipitation particles, as a result of which it loses its strength. In other words, it suffers from attenuation. So the problem was, can we use this amount of attenuation? Can we convert that quantification into the estimation of how much rainfall is present in that area? Now, this is a very attractive proposition because, first of all, this data is available through a centralized server through whichever company you're working with, through their servers all over the world. And then, unlike weather radars, which are very few in numbers, communication in Europe and 2 million worldwide, including in the developing economies. So can we use this attenuation information and then convert it into rainfall rate? So if you look into weather radar, because they are designed to sense weather, at the receiver, they have a host of useful information that you can use to estimate rainfall. So if it is a dual polarimetric radar, you can get an estimate of size and shape of the raindrops, intensity of rain. You can differentiate between hail, graupel, snow, rainfall, all those meteors. You can also get the Doppler velocity, mean Doppler velocity of the storm, and so on. And all of that is useful for rainfall rate estimation. But here all we have is this attenuation information, specifically specific attenuation, which is the first derivative of attenuation with respect to range. How can we use that? So we can, if we have to rely just on that, we are not going to get a very accurate estimate of rainfall. So what do? Many presentations days in electrical engineering and elsewhere, there comes a point in the presentation where you encounter deep learning. That is that point. It's not forced. It's actually very useful. It's an information scarce scenario. So what we are going to do, it with the nearest weather radar data, and then in the prediction stage, we'll feed it with the satellite link data and see what it gives us. So we did in the southwest part of Germany. In that box, you see about the black dot is a user type. And then we network that we train using the nearest German weather service or DWD radar. Now just for one the result, the bottom plot just use in what the neural network is giving us with respect to the DWD radar. Our goal is to actually improve this. But let's continue with this way for version. So we did this for all the terminals and then try to generate a range. For one storm, 2018, toward the north, and on the left side, slight network rainfall map that we got using this deep, and you can't match at all. Maybe similar, but for practical purposes, this is useless. For meteorologists, it has to match radar. So we wanted to improve. So this is for just 25 to 30 terminals. Now we know in learning networks it can be very helpful. So the next thing was that we got access to data from France, about 12,000 terminals. And then we did more and hyperparameter tuning with the neural network. We decided to change the network and then tune it a little bit more. And then we compared these 12,000 terminals, the rainfall map that we got with the Meteo France radar. Here is the result. Panel left is Meteo France. Now they match very well. And the bottom two panels is the, you can see satellite link now very well matches Meteo France radar. It's a move, another storm that 2020. You can see the which is intensity of the storm as well that you see there, 12,000 terminals. Sometimes those black dots of example of opportunistic ISAC. Here we train the network using, and then in the prediction stage we fed it with the communications data, and then the final radar. So we have done this for Germany, entire Germany as well. Results have been very for terrain. Extensions of this problem as well. This is using the satellite link coming from space in that case. So it to use the there is some, we have also done some work their own is the stadium. So use the base station to estimate where it thread radar data. So that paper was interest now. Have this quiet periods, and the aerial radar, if it is a military, 1 to 3. Tiered structure band, the highest priority. So signal, it is quiet, then you transmit. So it's again, you can repurpose your base station. You can PPP protocol, and you can use that to detect this aerial radar. Third one is, which we are these days, is to do ISAC sensing and communications. Sync is synergistic imaging and communications, which is what that advice intelligent systems works on. That can be used the base station signals or the communication signals and do the imaging of the environment. That is also a very popular area of work these days. So you can find those. There's many different ISAC architectures. I can't cover all of them, but if you're interested, I've listed some of them here, different types. The dual blind deconvolution, there's dual deconvolution as well. RAS aided, I talk about it. We have done a lot of work in that area. And as I mentioned, with OCDM, that is use of different types of multi-layer waveforms for ISAC. Some more architectures always be a source of interference. Sometimes it may have useful information about the radar target in the automotive scenario, and you can do sensor fusion to enhance the detectability of the target by combining reflections of both communication signal as well as your usual radar signal. And some other types of architectures. So to make here is, whenever we open spectrum for shared use, then the security of military radars and privacy. Because of that, there is a lot of focus in recent times on secure and privacy preserving ISAC. We have also done some work on this topic. So what is the future of spectrum sharing? So we are trying to become more efficient in the usage of spectrum. Does that mean that its usage will decrease? Answer is no. So there are these two famous in economics. Some of you may be aware of that. So I'm looking into economics more because we are working on a different problem of inverse cognition, where we use economic theories and apply it to cognitive radar, cognitive target scenario. I'll talk about it at some other time, hopefully. So in economics, there are these two theories. One is Gibbon's paradox, which says that if you're using a resource more, it's possible that it may become cheaper or available, and instead of actually the use may increase the usage of that resource because it is more available. And then there is another postulate, but then it posits it on this increased usage because of increased efficiency, because then you may have some new technologies or new usages of, again, you it more. So spectrum usage is actually increasing. If you have been following the news, then in US we had this one big beautiful act where about $88 billion are reserved for auction for a very small part of the spectrum. People are discussing, then we have to stop communications users from using it. The lobby share spectrum. So we are actually seeing new applications coming up in both radar and communications because of efficiency in spectrum use. So hopefully this will lead to some new signal processing problems as well in the near future. So that that golden dome thing is tied up with this aerial radar problem that I talked about. We have reached the end of this talk. So at the end of every YouTube video, you have share, subscribe, right? There's not a YouTube video, but my research, please feel free to connect with me on my LinkedIn handle, where I frequently updates about my new papers and upcoming talks. We published this book last year from Wiley IEEE Press, Signal Processing for Joint Radar Communications. You'll find a lot of information in that book that I didn't cover today. You might have guessed I have some interest in weather sensing. In fact, I worked on the topic for almost 15 years, and we published a volume compendium on advances in weather radar recently, which covers a lot of progress that has happened in this area. Now we are seeing more work from the signal processing community in weather radar, so it may be of interest to you as well. So with that, I would like to thank you for hosting. I'm happy to take any questions you guys might have. Thank you very much.
Thank you, Dr. Mishra, for a very interesting talk. I request the audience to ask your questions.
Yes.
Nice talk, thank you. I have two questions. So the first one is little general. So today the communication system is divided into several cells, and the cell planning is designed such that, if you want to require a minimum rate at a given cell edge user, that's the part of the communication system design. If you go to the radar system design, you again have a similar notion in terms of measuring a given range with so much of accuracy. So you can design these two systems independently using these two notions. But now when you want to combine both of them into a single hardware, will these design choices be compatible with each other?
Okay.
So that's the first question.
You want me to answer that first, and then we go to the. I get this question all the time, by the way, what you asked. Can we combine these two different metrics, right? And I think with Chandra, we had so much discussion on this. There have been attempts to combine them, and there's also a community which is completely against that. They would rather prefer radar-centric and communication-centric types of solutions because we don't get very accurate. So far, we don't have a very accurate output if you try to combine it. What are the methods to combine? Now, you mentioned the rate and the estimation accuracy. So if you look into Dan Bliss's work, he actually converts that estimation error into so-called estimation rate, so that you have two rates to work with, and then he tries to combine them. There are mixed results. Another way to combine them is to look at mutual information, which is right from Mark Bell's paper from Berkeley, right from 1980s, people have been attempting this, but for waveform design. You can also do it for the receive case. So mutual information in communications, we know about it very well. You can also have it in radar, actually. So he came up with that definition, then try to combine mutual information for radar and communications, and then try to design a system where rate constraints and this detection can be taken into account, although you cannot convert mutual information of radar directly to probability of detection. It's a very vague connection, but there are works like that to combine. And then there is a community which says that this cannot be attempted because the objectives of radar and communications are very different. I mean, communications are looking at bit error rate, spectrum efficiency, and so on. Radar is detection, estimation, classification, tracking, imaging. It's not proper to combine them, rather work on radar-centric and communication-centric solutions and have this tiered approach to the usage of spectrum. So there are some parts of the spectrum which is completely non-negotiable because of military usage. But military is not using it continuously. So if you have this tiered usage, when they're not using it, then shift to the communication-centric solution. So right now we don't have a consensus on either of them. These are two very strong communities. I also don't want to take sides in this case because there are pros and cons for both of them.
Sure. The other question is a little technical in terms of what you showed. So the first problem you had solved for a dual deconvolution operation, but even within a single deconvolution operation, you have when you don't know both the signals, you do have the identifiability issue. For example, you can scale one of them with one phase and then scale the other with the negative phase. They can still compensate. But now when you have a dual deconvolution, you have another stage of limitation in the sense you can add and subtract another constant terms to both the terms, and again you're going to have another level of non-identifiability issues. So how do you does your solution somehow account for all of these identifiability issue, or still there is a fundamental non-identifiability associated with this solution?
So, well, in any ill-posed problem, you can only solve it up to these kind of ambiguities, addition of constant. I mean, you take phase retrieval, depending on what application it is, you will have ambiguity in the global phase, you will have ambiguity in the rotation of the signal, and so on. Here also, you will have some ambiguity. You can only solve it until that ambiguity. But like I said, the more information we get that we can encapsulate in the structure, more accurate it could be. But again, you will have these ambiguities. Addition of constant will always be an ambiguity in blind deconvolution.
In fact, here you also have to associate which corresponds to communication and which term corresponds to radar. So again, you have an association ambiguity between the two terms.
Yes, but for radar and communications, the signals are different. So there is actually another problem in literature which is similar to this, which actually predates this problem, that is blind demixing. So in blind demixing, you have many convolutions which are superimposed on each other, but the structure of all signals, the corresponding convolvents like X or H in different convolutions, structure is the same. This ambiguity happens a lot more in that problem. Here, we are fortunate because the structure of two signals is different. You can do some association that this is the radar part, that is the communication part. Radar is pulse Doppler radar, communications is OFDM. That's why it is not like blind demixing. Is it easier than blind demixing or not? Actually, it is not. I mean, there are parts in the blind demixing that are difficult because of these ambiguities. But here, it is more complex because the structure is complex, but we have full knowledge of the structure. That helps actually in this case. Please.
Thanks for a wonderful talk. Very interesting. I just want to know, in the recent IEEE series of talks, space 202 point on that. They are talking about opportunity transmitters and receivers and multispectral. What are you trying to do here by doing this joint signal processing using the radar and communication? Are you trying to detect the target, or are you going to get some benefit from the radar towards the communication?
Well, the objective is that radar and communications transmitting in the same part of spectrum and hence encountering this mutual interference, we want to mitigate that mutual interference or despite them transmitting in the same part of the spectrum, we want them to function like normal radar and communications. Like radar should be able to detect, estimate, track, communications should be able to decode its messages. But in the same part of the spectrum, transmitting, receiving at the same time, at same frequency.
No, we were trying to declutter the environment, right?
Oh. Okay.
Is that so?
Well, depends on the application of radar, because if it is automotive radar, there is no clutter. You have to image everything, right? It's an imaging radar. So in automotive, clutter is not the issue. But it's not the clutter, because clutter you can model, right? I mean, all common causes of clutter, if it is weather clutter, we know you can model it with a Gaussian. Sea clutter models exist. This is interference, but interference which is continuous. In case of communications, in radar, if depending on what type of radar it is, it will have a different form. So it's not clutter. Clutter could be modeled. This is interference. It's more structured, but maybe known or unknown.
No, sorry for repeating this question. This interference, you are trying to avoid both ways, interference from radar to communication, communication to radar?
We have cases where we avoid them. We have cases where we also use them. So like I mentioned, this one problem where you can do sensor fusion. If you are getting interference, but it has some useful information about the radar target, actually use it together with radar. So the problem is really not just looking at the interference as the bad guy. Sometimes it can be useful. In opportunistic ISAC, it is useful all the time. And we are using communications and then trying to either complement radar observations or trying to combine it for a radar purpose. So yeah, it is both ways. If it is bad, then you work on mitigation, but it could also be useful, then you have these new kind of applications.
Last, regarding this, your handbook on statistics 55.
It's not related with this. So.
Okay, anyway. So I'm just taking a cue from that. You are saying multi-dimensional signal processing.
Yes.
How does multi-dimensional differ from the multispectral signal processing?
Multispectral is a type of multidimensional signal processing.
Oh, I see. Okay, thank you.
Yes.
You have discussed two waveforms for sensing, like PMCW is better for range estimation and OFDM is for velocity estimation. So I want to know, and you have worked on OCDM also. So I would like to know like which waveform is best or like optimal. Is there any way to find like optimal waveform for sensing? There are many waveforms.
So if you just say optimal waveform for sensing, there are thousands of papers on that topic, right from the development of radar. But if the question is which one of the multi-carrier waveforms is good, of course OFDM is very, very popular and for good reasons. There are a lot of implementations and so on. And then with OCDM, and between OFDM and OCDM, there's also another one, which is OTFS. There's a lot of work on that topic. And as you go from OFDM to OTFS to OCDM, we see improvement in the PAPR performance. Now here, that is for the communications aspects, right? Here we are using them for both joint radar communications. What we have seen, and Chandra is also here. So with OTFS, and there's a lot of work on that topic, we don't see any improvement in the sensing performance. People use it for joint radar communications, but if you look at the papers, the sensing performance is almost same as OFDM. It's in the very first paper also by Giuseppe Kayer and Mari Kobayashi. There's no difference in that, but they are motivating the use of OTFS for joint radar communications because at least the communications performance is good. And then OCDM, at least there's one use case in the work that I listed here with Chandra, where there's some improvement even in the sensing performance. Now, which one is better? So in radar and communications, because objectives and applications are so different and so diverse, it's just very difficult to give an answer, okay, this is better, because I don't know what is the criterion you have in mind. If you're thinking from the implementation purposes, OFDM has a lot of hardware that is available, right? If you are interested in improving the communications performance only, but want to use a better multi-carrier signal, then go for OTFS OCDM. But if you're interested in mostly sensing performance improvement, then you can just stick with OFDM, you know. And then there's a question of whether we should design a new waveform or not. That depends on the industry. Automotive industry doesn't prefer that. But you know, if the goal is to get a paper in information theory transactions or DEVCOM, then yes, by all means you go ahead. So it's difficult to give an exact answer. That is why we have so many different types of ISAC topologies, because we have many different types of communication protocols and requirements. We have so many diverse radar systems. You want to combine one of them with the other. Usually it leads to a new ISAC design, you know. So it's very difficult. That's a short answer. It depends on your requirements.
I now request Professor Chandramurthy to hand over the memento on behalf of IEEE student chapter.
Thank you. Okay, you got that background? Okay, thank you. Thank you very much.
Thank you everyone for attending. We have arranged refreshments in the coffee hut. Please continue your conversations there.